We're here with Nick Sitar of the Earthquake Engineering Research Center. We want to know, we're in this incredible facility. It's huge, it's beautiful. What actually happens here?
Well, this facility is operated by the University of California to provide researchers with access to major testing equipment. And we have a shaking table facility, and then we have a hybrid simulation facility which is funded by the National Science Foundation. What happens in an earthquake is relatively simple in the sense that the ground moves and the building moves with the ground, and because the building has a certain amount of mass, that mass, the inertia of the building, then produces forces within the building. And it's those forces that then can cause failures. And so what we have to do is design the building to move in such a way that either doesn't couple with the ground motion or it can resist the forces that are generated. There are several different technologies that are used. Base isolation, as it is called, to isolate the building from the ground motion is one approach that's being used, and it's being used more and more, not just for buildings but also for bridges. And basically, like shock absorbers in a car, they allow the building to remain relatively stationary relative to the ground. One of the things that most people don't immediately think about is once you put a building on base isolation, the building is going to move relative to the ground. And so now you have to provide space between the building and surrounding ground. So a building like that would be surrounded by kind of a moat, if you want to think about it that way, that provides the separation between the rest of the ground and the building foundation. Now, what it means is that all the utilities and all the connections to the building have to be flexible so that they can accommodate all that motion. One of the basic tools that we use in our laboratory is the shaking table, which is just a large, in our case, concrete platform. It's 20 by 20 feet, and it can move in 3 directions. And we apply actual ground motions recorded during earthquakes. But there are things that you don't see. For example, the way bracing is applied, even in wood structures, the way reinforcement is placed in concrete, the type of concrete that's used. So there are a lot of other things that may not be all that visible, which all represent technological changes.
So what's this huge machine behind us? What kind of experiments are done on that?
Well, this is a 4 million pound compression machine that was actually built in 1930s to test large building components. And we have incorporated it into our hybrid simulation laboratory to be able to simulate full building loads on things like columns in buildings. We do a lot of computer modeling. In fact, a lot of what we do applies directly to computer simulation. But because a lot of these structures are very large and they're unique in their shape and in their dimensions, we cannot quite simulate everything directly. And therefore, we need to have some experimental data to back up the simulations or to allow us to do the simulations. So what do you do if you're a typical worker in a cubicle in an office space where the door frame is very far away? Well, it turns out that the acoustic ceilings and the lights above you are probably the biggest danger to you. So diving on the old adage about diving under your desk is still the best advice that can be given.